Yeah, thank you. Welcome to the talk. I'm Mikko Kytö from Aalto University, and I will present our work that was done with Barrett, Gunn, Tham, and Mark from University of South Australia. So the title is Pinpointing Precise Head and Eye-Based Target Selection for Augmented Reality. Here's an overview of the talk. First, this basically explores pinpointing. It's a multimodal head and eye gaze pointing technique for wearable AR. We develop and evaluate a lot of different techniques. And after developing and evaluating the techniques, we developed two design implications for user interfaces, such as target sizes for different pinpointing techniques. And then we provide two potential applications for pinpointing. The first one is called Gaze Browser. It's basically a precise menu selection technique. And the other one is called SmartPupil. It's a correction method for removing calibration drift. So first, let's have a look what pinpointing means. So it consists of two phases of primary pointing and refinement. So let's say that we have a target in the scene, shown here as a green cross, and we have a cursor that we need to align accurately with the target. So first, we use a primary pointing to make a course selection which approaches the target, and then we make a refinement selection with more precise technique accurately to select the target. So there's two different phases in the technique. So motivation for pinpointing. We believe that many wearable AR applications in the future will require precise selection and interaction, such as interacting with CAD and architectural models. However, users to be more productive and mobile, we need to do this without bulky input devices. So head and eye-based techniques are promising techniques in that sense, as they don't necessarily require external devices to be carried, and they are like mobile approaches. So let's have a look first at the state-of-the-art technique, which is head pointing. Head pointing is basically based on the rotations that users do with their head, so they point their forward towards objects. It's fairly accurate, although not as accurate as mouse, and it's quite stable, so more stable than eye movements. There are two main challenges for head pointing. The first one is called Midas touch problem. So everything that we point with our head, we don't necessarily want to select. And the other one is it's a bit unergonomic, so that users need to rotate their head continuously. It can cause like neck pain in long-term use. The other one, eye gaze. It's potentially very fast input technique for AR. It's more ergonomic, as we are used to interact. We are used to move our eyes quickly and frequently. But there's two major challenges related to interacting with eye gaze. The other one is accuracy. The accuracy of current eye tracking devices is not very good. And the other one is similar to the head pointing, are the involuntary selections. So basically we don't want to select everything that we look at. So these techniques, we couple these head pointing, eye gaze with refinement techniques. And the first head pointing with refinement hasn't been investigated to the best of our knowledge before. The situation different for eye gaze with refinement techniques. There's various studies looked into this. The classic work is by Chai, who refined eye gaze using a mouse in desktop environments. And then this work refined eye gaze position using a touchscreen, handheld touchscreen. And this used refined gaze on a tablet, so the user looked at the point in the tablet and then was able to make the refined selection using a thumb. And this work investigated using refining eye gaze with head movements in virtual reality. But there's less work in wearable AR and less work on exploring more different techniques how to refine eye gaze. So let's have a look at first the studied refinement techniques. The first one is refinement with hand gestures. The strength is that no external devices are needed, but the challenge is that the detection rate is not 100% perfect, and hand gestures can also become tiring if users have to have their arms lifted in front of the head-mounted camera for a longer time. The other one is refinement with hand controllers. So they are more reliable than gestures, and we are used to press buttons quite well. Well, the obvious drawback is that users cannot have their hand for other tasks, and external devices needs to be carried. Then a third technique that we use in this paper is a refinement with head motion. So basically, we changed the control to display ratio above 1, so above 1 to 1. So in normal mode, the user's head motion is straight mapped to the movements of the cursor, but we can just make it more, increase the control to display ratio so that the user needs to rotate their head in order to achieve the same cursor movement, making the selection more accurate. So to investigate these different techniques, we designed a study where we had two primary pointing methods, eye gaze and head pointing, and refinement modes, none, which was the baseline condition, and gesture, device, and head. So the study setup, basically we used the target selection task. We used 8 different directions for the targets, and we used 2 different distances for the targets. Some of the targets appeared here on the outside of the field of view, as we wanted to investigate what's the effect of having the targets within field of view and outside field of view. And this is the field of view of the HoloLens, so you can see that some of the targets appearing outside field of view and some of the targets within field of view. We used HoloLens with the Pupil Labs eye tracker, and we had 12 participants that had at least intermediate experience with AR. So all the participants did all the 8 conditions, and we collected accuracy, time, preference, task load with NASA TLX measurement and subjective feedback. In this presentation, I will concentrate on accuracy and time for time constraints. Here are still examples of how actually the experiment looked like. So this is eye gaze with gesture refinement. So in this case, user looks at the target and then makes the refinement with a gesture. The eye reticle shown here wasn't shown to the user, so it was just for visualization purposes. So the tap gesture activates the refinement mode, and the user refines by moving the cursor to the target. And here's another example. And then, similarly to the previous method, we refined, did a similar thing, but refined the eye gaze with device. So again, user looks at the target, but now rotates the device towards the target to make the refined selection. And then third example is head pointing with head refinement. So in this case, users point their heads towards target and use head motion for refinement. You can see they're rotating their head towards the target. Yes, and let's go to the results. So we evaluated each technique in terms of accuracy and time. And first, the baseline conditions, eye-only condition was fast but less accurate, and head-only condition was more accurate but took longer. Then, with the refinement conditions, eye-based refinement conditions, we were able to achieve the same level as the head-only condition, although it took longer for users to select the target than with head-only condition. With head-based refinement techniques, the accuracy was drastically improved to the head-only condition. It took a bit longer time. The head plus head that I showed the example was actually the most accurate and the fastest of the refinement techniques, head-based refinement techniques. And when looking at the accuracy of looking more at the accuracy of head-based conditions, you can see that the head-only condition, which is like the state-of-the-art technique, for example in HoloLens, with that you can achieve like a 0.3 degree accuracy. But with, for example, with this head plus head condition, the accuracy was improved to be 0.1 degree. So the accuracy was 3 times better. And then we defined target sizes for each technique. So based on the distribution of the values, we computed this rectangular and circle targets. And you can see that with the eye-based, with eye-only condition, the diameter of the target should be as large as 16 degrees. So that was very large. And we found out that this was partly due to the drift of the calibration tracker, and such as these values are a bit larger than found in previous studies. So this there's need to develop more accurate techniques to remove the drift in the future, but I will come to this part later in the work. So then we showed 2 applications for pinpointing. The first one is gaze browser. So this is for accurate for accurate menu selection. Here's an example video how the gaze browser works. So the user can look at the menu and then make the menu selections using refinement techniques. And we can use very small items in the menus. The head reticle is visualized there as a green dot there in the video. And there's a slow motion of user selecting very small targets in the screen. The other technique was called a SmartPupil. So basically it's a technique for like online calibration improvement, and it can be used to reduce drift from the eye trackers. So here is the basic idea how it works. So first, user looks at the target here, but because of the inaccuracy of eye tracking, the eye gaze appears far from the target. But we can take this error between the between the eye and the measured eye, and use the correction vector for next trial to improve the guess where the target is, so that the cursor is moved towards the target with each trial. So we can use the error vectors from previous trials to move the cursor towards the target with each trial, and so on. Here is it working in live. So this is how it looked like. So without a smart pupil, the cursor appears at the same position as the eye reticle, and it's for the refinement, it's difficult to reach the target. But with a smart pupil correction, the accuracy is improved with each trial, so that refinement starts closer to the target. Yeah, and we found out that this improved a lot the accuracy of the refinement distance was much less, and we were able to remove the drift from the tracking. And when we compare this result with the first study, if we can reduce the refinement to start much closer to the targets, we can actually achieve faster eye-based refinement techniques. So, but this is part of the future study. So to conclude, I showed adoption of multimodal techniques for wearable AR for improved accuracy, and we made a broad comparison between different techniques, and we attained the precision to be below like 0.2 degrees, and we showed two potential applications for pinpointing called Case Browser and SmartPupil. Thank you. That was the end of my talk, and actually my co-author Barrett, who is also here, is looking for PhD students to join him in University of Monash University, and I'm as well actually looking for new positions after this year. So come talk to me, and happy for questions. Thank you.
Congratulations for the Best Paper Award. I'm Shumin Jai from Google. I wonder how, so back to magic pointing, I don't quite remember the details, this is about 20 years ago now, but the motivation was certainly to make the eye gaze, or in this case head pose, these as more as context to the system rather than as explicit input. So the users is as little aware of their eye gaze role as possible. In this context, in your application, you seem to actually make the cursor explicit, or is that just for the demo, for us to see? Does the user actually see the dots when they actually use it?
Yeah, no, they didn't see it, so we removed it, yeah.
Oh, okay, so,
yeah.
so they are not aware of that?
Yeah.
But overall, did you feel there's still like a transition or hand-eye coordination kind of effort? That was another goal we want to minimize. That is, they should not be aware the mechanism. But in this case, do you feel, I don't think we necessarily achieved that 20 years ago, but do you feel with today's technology, a user, did you achieve that? That is, the user are not aware of the eye gaze or the head pose, but rather it just feels like a very intuitive, natural.
Well, in the comments we got from the participants, it felt natural. The eye gaze was, they were preferred equally head and eye. So, but it was in the subjective feedback we collected, they found it to be a natural way to interact or select objects. And for the hand coordination between head and eye, The head and head was fast technique, maybe because you didn't need to change your modality. So you could use head also for refining and head for pointing. So you didn't need to change like your modality.
In a ballpark, how does it compare to, say, like commercial remote TV control kind of functions? Because the time performance looked not very competitive. It's like from 1.5 to 3 seconds. That's a pretty long time for single trial pointing. So in your view, how competitive such techniques is practically in comparison to what's being practiced in remote pointing?
Well, we didn't compare it to the pointing with the device like raycasting pointing. So it's difficult to say. Actually, it's a good question to look further.
Okay. Thank you.
Yeah. Thanks.
Hi, Mikko. Mathieu Nancel in Lille. This great work, really thorough. First, I would like to say there has actually been some work on head plus refinement. We have one Karin Wan-Chokai paper that might be interesting. So my question was about performance. So you have this graph of performance that separates techniques per their input channel, but as soon as you get to relative pointing, there's going to be a huge effect on transfer functions, gain functions, how you translate that. Could you tell us a bit more about how you design those for your techniques that use relative pointing?
Yeah, good question. Basically, we used the pilot study to find out the different values for the gain, but that's a very good further work part to investigate more deeply different gain functions.
So that was fixed gain?
Yeah, there was fixed gain, yeah.
Thank you.
Yeah.
Okay, let's thank our speaker again.